Okay, looking at an application problem here. An airplane flies due east, 500 miles per hour. So we can envision a vector, 500 miles per hour going due east. Component-wise, that would be the vector 500, comma, 0. The tip of this arrow would be 500 units to the right of the origin. And of course, due east is an angle of 0. A 70 mile per hour tailwind would be a 70 unit long arrow making 60 degrees north of east. Breaking this into components, we could actually go back to the 30, 60, 90 right triangle to save us a little bit of time. Opposite of 60 is a root 3, opposite of 30 is a, opposite of 90 is 2a. So we could see that this would be 35 for the x component, 35 root 3 for the y. So very, very quickly we have our components. So we have a tailwind pushing an airplane. Airplane's going 500 miles per hour. Obviously, there is a change in the direction, a change in the speed that we're going to see as well. The resultant vector is going to be found simply by adding the components together. That would be 535, and 0 plus 35 root 3, of course, is just 35 root 3 itself. So what we're seeing is this. This airplane is going to be on a new path. You can see that 535 is our x component, our y component is 35 root 3. What's our new ground speed? Well, our new ground speed, you could call that r up here. We can use the Pythagorean theorem. 535 squared plus 35 root 3. Squaring that, and then we could certainly let the calculator come to our assistance. Let's real quickly type in 535, square that, plus then we'll have 35 root 3, and oops, you know what, let's bring that back a little bit. And square, oops, having a bit of trouble here with these parentheses. There we go. And square that. You can see we'd be at 289,900, but we'll take our square root of that. Second answer. And we'll see it's about 538.423. And using AP rounding, we'll go to 3 decimal places. We could also have rounded that last part up, 538.424. So you can see the wind has changed the speed of the airplane. Not only has it, changed the speed, it's also going to change the direction. So this could be called the ground speed. We could say, well, what about the direction? Well, that's theta. Very quickly, we could say the tangent of theta is equal to opposite over adjacent. So that's 35 root 3 over 535. And we could do an inverse tangent of that. Maybe we will change our mode real quickly to degrees. And just get this typed in. So we'll see what's happening here. Let's change our mode back to degrees just for a second. Do a second quit. Okay, so we'll say second tangent, inverse tangent. Here's our 35 root 3 and divided by 535. see very quickly we have about 6.464 or about 6.465. So that's 6.464 degrees. Could also round up. Both answers would be accepted. But that's that many degrees north of east. So what we're seeing is this wind has not only changed the ground speed, or the speed of the airplane, it's also changed where it's headed. Real quickly, let's take a look at calculus. From the calculus standpoint, we're going to stick with working with components. And for a position vector, you can see r of t, a position vector, will be written as a vector in components, x of t, y of t, where t is representing time. Now the wonderful thing is, as you look at x of t and y of t, it sure looks like it's written parametrically. And the wonderful thing is you can interpret it that way as well. Parametric topics are going to be converging here with vectors as well. But taking a velocity vector, we'll just take derivatives of components. We'll get dx dt comma dy dt. If we wanted to take the speed, though, we'd have to take the magnitude of v. So speed is going to be, using the Pythagorean theorem, the square root of dx dt squared plus dy dt squared. Okay, taking an acceleration vector. Again, we're having a vector. That's going to be the second derivative of x with respect to time, second derivative of y with respect to time as well. Direction of motion is the direction vector, if they're ever asking us to find that. That would be the vector divided by its magnitude. This will always have a length of 1 when you have a direction of motion vector. Absolute value of v is the magnitude of v, so you're dividing that out. You'll just be left with a direction vector of length 1. Let's very quickly take a look at the last two problems. You can do them very, very fast. Looking at example 5, I want to first point out that sometimes instead of using those pointy brackets, you can use regular parentheses. They're used interchangeably. But regardless of how it's written, you can represent a vector with respect to time here. Find the velocity vector. Well, the velocity vector, take your derivative of your x component, the derivative of sine is cosine, with respect to t, you'd get cosine of t. Derivative of t squared all over 2, we'll bring down the 2, you have 2t all over 2. That's leaving you just with the t. We are done. The acceleration, and you could call this v of t if you'd like, the acceleration vector with respect to t. Well, take your next derivative, the second derivative. The derivative of cosine is the opposite of sine t. The derivative of t itself is 1. And wow, would you look at that, we're done. Last problem, for example 6. A particle moves in an elliptical path. You're given that x of t is equal to 4 sine of t. You're told that y of t is 2 cosine of t. This is going to be very important in just a moment. But first, let's go ahead and find the velocity and the acceleration vectors. Hopefully that we can do very fast. Derivative of our x component, derivative of sine is cosine. So very quickly we'd get 4 cosine t. Derivative of cosine is opposite sine, so we get negative 2 sine of t. Let's very quickly find our acceleration vector. Take the derivative of cosine, we have the opposite of sine. And like we said earlier, the derivative of sine is cosine. So you can find velocity vectors and acceleration vectors incredibly fast. Let's take a look at part B. They want the velocity at t equals pi over 4. And they want that written as a vector. Velocity is a vector, something that we want to think of. So here's what's going on. They're saying, what's v of pi over 4? Well, v of pi over 4 is going to be 4 cosine of pi over 4, comma, negative 2 sine of pi over 4. Well, you know that both sine of pi over 4 and cosine of pi over 4 are root 2 over 2. So I hope it's not too much of a jump to see that the 2 cancels with the 4 here. The 2's completely cancel out in this regard. You just have negative root 2. And here you go. It's 2 root 2 comma negative root 2. They do want the speed as well. And normally I'd jump right over to acceleration, but speed at t equals pi over 4, well, that's going to be the Pythagorean theorem. That's going to be the square root of 2 root 2 squared plus negative root 2 squared. And 2 root 2 squared, well, that's going to be 4 times 2, which is 8. And so we've got the square root of 8 over here. The radical 2 squared is just a 2. This simply becomes radical 10. This is not written as a vector. This is actually a scalar. Real quickly, we could find out what a of pi over 4 is. This is going to be more or less plugging in pi over 4 into that last part of part A. So a of pi over 4 is a vector, and we can see it's negative 4 sine of pi over 4, negative 2 cosine of pi over 4. So very much what we've got is, again, these are root 2 over 2. So you could see that this is negative 2 root 2. Negative 2 times root 2 over 2. The 2's cancel out. You just have a negative root 2. So that's your acceleration vector. Sketching a path and answering whether we are going clockwise or counterclockwise, please do take your calculator and change your mode. Let's first make sure we're back to radians. But go to parametrics. Going to parametrics will allow you to enter in our original position vector parametrically. We have 4 sine of t, 2 cosine of t. The largest x could ever be would be a 4. Sine can only be as big as 1. So I'm going to have my x min and max go between negative 4.5 and positive 4.5. Cosine can get as big as 1, so 2 times 1 is just a 2. So real quickly, I've made my t min 0, my t max 2 pi. I'm going negative 4.5 to 4.5 here for the x, negative 2.5 to 2.5 for the y. And again, just graphing this, you can see, as they told you, it's an ellipse. If you look at how it was graphed, it's actually going to be graphed in a clockwise fashion. So what would this graph really look like? Well, we can see very quickly that from help with the calculator, it's an ellipse. It's looking something like this. It starts this way and it's going to be going this direction. We can see from how it was graphed that it's going clockwise. But there's a little bit more that we have to talk about. They want us to find the velocity vector at 4, 0. At the point 4, 0, we need to remember what x and y were. X was 4 sine of t, and y was 2 cosine of t. So if I were to substitute those x and y coordinates in, we can see super quickly that we'd be solving for when sine of t is equal to 1 or when cosine of t is equal to 0. In either case, we're solving when t is equal to pi over 2. At pi over 2, we're going to be able to actually find the velocity vector. I'm going to have to let off for right here, and we'll finish this up in a little bit.